So our next portion of this is going to transition us from Unit 4, which is magnetism, to Unit 5, which is electromagnetism. The names are largely interchangeable. There's not a whole reason why they named them the way they did. But we're going to cover 3 pieces of information and potentially a fourth. First, Faraday's law. Faraday's law is an extension of motional EMF, which is what we're going to talk about today. But in addition to Faraday's law, we're also going to talk about what's called Lenz's law. Lenz's law is an application of conservation of energy, and is it's funny that it's not covered necessarily by Maxwell's law the way you'd like. By Faraday's law the way I'd like, but it's there. It's just that Lenz provides some context for why it's there. After we're done with that, we're going to talk about inductance and inductors. Got a couple of labs about that, because then we're going to talk about LC and revisit RC and then LRC circuits. With this one, unfortunately, requiring us to do a new kind of differential equation. So we'll see how that goes. But I'm hoping to kind of time it right when mechanics is getting into simple harmonic motion, so that they'll have the same kind of stuff happening in both classes. And then we will end with Faraday's laws. No, Maxwell's laws. So that's what this last unit's about. This is huge. It's on the exam. When I say on the exam, it's about 25% of exam content tends to boil down to Faraday's law. It will be presented on the exam in multiple places. It could be in more than one FRQ. It's big. Inductance and LRC circuits, pretty small, 10 to 12% chance of showing up on the exam. They tend to favor RC circuits over inductor circuits, so it's not uncommon. I'm sorry, I put LC there, but I should have put LR circuits. LRC circuits, I've seen 3 LRC circuits ever on the exam. They do have a lot of circuits where they pull out a capacitor and replace it with an inductor. That's pretty typical. Maxwell's laws may or may not be on the exam. I don't care. You should not leave an E&M class without knowing what Maxwell's laws are. So we'll cover them. We'll spend only about 3 days on it. I will make up homework questions related to it, because there won't be any in our books or any in our exams, but I want you to have some experience working with Maxwell's equations. So we're going to start with motional EMF. And the concept is not hard, and I like it because it's pretty straightforward. I want to define a few things. First, let's imagine I have a region of space with a magnetic field that is into the screen. Like so. And then I take a conducting bar and place it just outside of the region of space with the magnetic field. So there's a kind of a barrier right here between where the bar sits and where the magnetic field is. Okay. If it's a conducting bar, that means that the bar would be full of charge-carrying particles. And those charge-carrying particles are free to move under the demands of a force that either is an electrical force or a magnetic force. Right now, in the circumstances that we're in, those charges should be distributed evenly around the conductor, because it's not being influenced by any electric field. What I want to do is give that bar a bit of velocity so that it can enter the region of space where the magnetic field is. So advance just a little bit. And let's say that the bar now makes it into a region of space where it is surrounded by this magnetic field and still experiences a velocity to the right. Now, this is the point where you have to decide whether you're going to be okay with these being positive particles. If you're not, treat them as negative particles. It's not going to make any difference. But we say that the charge-carrying particles are positive. And under this circumstance, the charge-carrying particles in this conductor are going to experience a force. And that force is going to be upwards on the positive charge carriers in the bar. Use your right-hand rule and make sure that you believe me. So I got it wrong once today. Don't want to get it wrong again. We all on board? Ah, good. The size of the force on the charge-carrying particles is going to be QVB. And I don't have to worry about the sign of the angle because I'm moving perpendicular to the field. And if we say that these are our standard charge carriers, then it's going to be EVB, because we're talking about the charge on the electron or the charge on the proton. You know, those are our charge carriers. So as the bar moves through this region of space, those particles are going to begin to group up in areas of the bar until such time as the forces are balanced. Now, this part you're just going to have to, I don't know how you're going to draw this, but if it were me, I'd want like little sections, so you know kind of how it's going. But I'm going to start to get a collection of positively charged particles at the top of the bar, and I will reveal available negatives at the bottom of the bar. The particles will move until the electric field, which there's an electric field now built up in the bar in this direction. The size of that electric field is going to depend on how many particles are grouped up at the top or bottom. But remember, the particles will only be able to move to the top and bottom of the bar while there's an unbalanced force acting on them. So basically, the electric field is going to reach a field strength where the net force on the particles will become zero and will reach a steady state condition. Everybody okay so far? That steady state condition is going to be when the electric force is equal to the magnetic force on those particles. Now, we've seen this before, but in this case, that electric force is going to be E times E, the electric field in the bar, and that'll have to be equal to E V B, the magnetic force acting on those same particles. Now, we're talking about the same particles, so those go away, and this tells me that the electric field in the bar will be equal to V times B. Now, we're dealing with a uniform conductor. It's not outrageous to think, then, that the electric field inside this bar will also be uniform. And if it's a uniform field inside the bar, then that suggests that there will be a potential difference from one end of the bar to the other. By definition, potential difference is the integral of E dot dx. If the electric field is uniform, then this potential difference is going to be E times D, where D represents the length of the bar. Right, just doing the integral, pulling E out because E is a constant, and integrating from one side of the bar to the other, or one end of the bar to the other. Now we have an expression for the size of that electric field in terms of the magnetic field applied. Which produces this kind of curious result. The potential difference produced in the bar is dependent upon how fast the bar how fast the bar passes into the magnetic field. It only exists while the bar is passing through the magnetic field. The moment it leaves the magnetic field, those particles are going to redistribute themselves because they will electrically repel each other until they spread out over the whole bar. But during the time that the bar is traveling through the magnetic field, a potential difference is produced. This might as well be a battery that is produced inside the magnetic field from the motion of the conductor inside the magnetic field. This can be used to push charged particles around. Now, unfortunately, it was given the name electromotive force, and EMF is stuck. Nowadays, they wouldn't use that phrase if they were naming it, but that's the phrase that's stuck. And we call this a motional EMF, or emotional electromotive force, but most of the time, we just say it's emotional EMF. This will occur for all conductors passing through a magnetic field. So all of our satellites orbiting the Earth all generate an electric potential from one end of the ship to the other. It all depends on making sure that they pass through the magnetic field. So some of our things that are orbiting are passing one direction through the magnetic field, generating one kind of electric potential, and some are generating the other. You launch a rocket into orbit and you want it to dock with the International Space Station. You have to discharge your rocket first and discharge the space station first. They don't talk about how that's done, but it's generating an electric potential across the spaceship all the time. NASA has actually tried to experiment with using this to generate electricity for satellites that are in orbit, since they're passing through the field all the time anyways. The problem is that, as you can probably imagine, the magnetic field is very weak. And to have this, you are already traveling very fast, but this number is very small, so you need an electrical array that is very big in order to do so, and it's hard to keep a large array rigid as it passes through the magnetic field. So it's not a viable way of actually generating electricity for satellites, but it is 100% how all electricity is produced in this country. This is how it's done. Now, we don't necessarily move a huge conductor through a magnetic field like this, but this is how we are generating potential differences. This is what the potential difference is that's in the wall right now. It comes from this. Now, I want to talk about how it's done in real life. This just generates a potential difference across a bar. How do you make it useful? Well, that's what I want to talk about, is how do we make this useful? But motional EMF is a real thing, and it's something that you should be aware of. Moving through a magnetic field, any conductor moving through that magnetic field is going to generate a potential difference. And so we start this by initiating a velocity. So this whole rectangle is going to move into the region of space where there is a magnetic field. Now, nothing happens until the bar passes into the region of space where there's a magnetic field. The moment that happens, we know suddenly that there's going to be an EMF from the top of the bar to the bottom of the bar, and it is dependent on how big the bar is. So this value D or L or whatever they use in the problem, be aware of it. Now, the moment that happens, we get a potential difference, which is equal to VBD, right? How fast we're moving, the size of the magnetic field, and how big the bar is. Now, this is a potential difference, so if we pass a resistor connected to both sides of my potential difference, I should be able to generate a current based on this. Now, a couple of points I want you to know. The book will no longer use delta V. They're going to use a script E here to stand for EMF. As it's not a potential difference generated by separations of charges using a chemical reaction, EMFs generally refer to potential differences generated by a magnetic field. So from now on, we will start using this. We'll pick this up tomorrow.